For the first question on the 2015 AP exam, it says metal air cells are a relatively new type of portable energy source consisting of a metal anode, an alkaline electrolyte paste that contains water, and a porous cathode membrane that lets in oxygen from the air. A schematic of the cell is shown above, and reduction potentials for the cathode and 3 possible metal anodes are given in the table below. So if you look at the table, the first half reaction is the oxygen reaction for the cathode, and the zinc, sodium, and calcium are for the metal anode possibilities. So if you look at part A, it says early forms of metal air cells used zinc as the anode, and zinc oxide is produced as the cell operates according to the overall equation below. Using the data in the table above, calculate the cell potential for the zinc air cell. So if you look, this would be the O2's forward reaction on the table and the zinc's reverse reaction on the table. So if you look at the table, the oxygen is in the forward reaction right now, so you would take that cell potential, which would voltage would be 0.34, and you look at zincs, and you'd have to reverse that because zinc is alone here as a reactant, and here it is a product. But you would also have to multiply that reaction by 2 because the electrons being transferred are not equivalent. So when you add 0.34 to 1.31, the total voltage would be 1.65 volts. Looking at part 2 of part A, it says the electrolyte paste contains OH negative. On the diagram of the cell above, draw an arrow to indicate the direction of migration of OH negative ions through the electrolyte as the cell operates. Since the hydroxide is negative, it would be produced at the cathode on the right. So as the cell operates, the OH would move to the left because it would be used up in the anode. So that's why I drew my arrow going left. In part B, it says a fresh zinc air cell is weighed on an analytical balance before being placed in a hearing aid for use. As the cell operates, does the mass of the cell increase, decrease, or remain the same? So looking at the cell, oxygen is obviously in the air in the beginning of the reaction, so this would cause the mass to increase. Part 2 asks you to justify this, and I would justify this by saying the O2 was not a part of the cell before, but as it reacts and as the cell is running, it would become a part of the cell and be incorporated into the zinc, increasing the mass of the cell because it was in the air before, but now it is actually considered to be a part of the cell's mass. Looking at question C, it says the zinc air cell is taken to the top of a mountain where the air pressure is lower. Will the potential be higher, lower, or the same as the cell operates at the lower elevation? So, the cell potential at the top of the mountain would be less than the cell potential at the bottom of the mountain because since there is lower air pressure, there are less O2 molecules present, and the partial pressure of that will be lower, even in the reaction of the cell as the zinc is being produced. So the O2's partial pressure would be less, so there would be less collisions. This would lead to lower cell potential because we know that the more collisions there are, the more cell potential. Looking at part D, it says that metal air cells needed to be lightweight for many applications. In order to transfer more electrons with a smaller mass, sodium and calcium are investigated as possible potential anodes. A 1 gram anode of which of these metals would transfer more electrons, assuming that the anode is totally consumed during the lifetime of a cell? Justify your answer with calculations. So if we look at part D, we would need to use dimensional analysis to figure out how many moles of electrons are being transferred by each metal to find out which one we would choose. So if we look at sodium, you would place the 1 gram, since that's what they gave us in the question, over 1, because that's what we always do for dimensional analysis. And then you want to find the moles. So you could separate this into 2 equations, but I put it into 1, and you'll see why. So finding the moles, you put 1 mole over 22.99, because that's how many grams are in a mole of sodium, and and then you don't have to stop there, because we do need to figure out how many electrons are being transferred. So on the top, you would put 1 mole of electrons over 1, and you would get 0.043 moles of electrons being transferred with Na. So looking at calcium, we would do the same setup. So you put 1 gram of calcium over 1, and then to find the moles, you would put 1 mole of calcium over 40.08 grams. And then keep in mind that with calcium, you would have to put 2 moles of electrons, because if you look at the cell half reactions, that's what you need to do. So you'd put that over 1, and I got 0.050 moles of electrons being transferred. So that means that calcium would transfer more electrons, assuming that the anode is totally consumed during the lifetime of the cell. So for the last question, it's pretty easy. It said, the only common oxide of zinc has the formula of ZnO. Write the electron configuration for Zn atom in the ground state. So using the noble gas shortcut, argon is the last noble gas before zinc. So I used argon, and then there would be 4s2 and 3d10. So the next part of that question says, from which sublevel are electrons removed when a zinc atom in the ground state is oxidized? So for that, I got the 4s sublevel, and here's why. We know, according to Aufbau's principle, that the 4s orbital is lower in energy than the 3d orbital, and it is filled first, unless it is a transition metal, which zinc is not. So that would cause the oxidation to happen at the 4s orbital sublevel, because there's less energy, and removing electrons, it would be more simple and easy to remove it from the 4s orbital. So that is what happens here. That is the end of the questions.